Okay, so I'm just going to give you a very broad perspective on the basics of transformer technology, engineering, terminology, so you get an idea as you listen for the rest of the next 2.5 weeks as to what all are we talking about here. So there is a drawing here that we will see. It will come up in a little bit later, so we'll just wait for that. Voltage is one of the parameters of electrical systems, and the voltage is of course in the does it scroll with this?
No, sir. It
okay
work through PowerPoint.
Okay, so then voltage, and then voltage can be expressed in volts or kilovolts. Mostly we use kilovolts because we go in the higher voltages. So the voltage in your outlet plug in your home is 110 volts. However, we deal with volts which is starting at about 480, and then we go all the way up to almost 1000 kV. So it's 100,000 volts basically. 1000 kV, no, it's 1 million. Sorry. So it goes that high. So this is kind of gives you an idea. 1 kilovolts is equal to 1000, and 13.8 kV when you say it's 13,800 volts. So that's how we label our voltage. And the designations is in the industry, something which is called low voltage to us is less than 600 volts. So anything less than 600 we say is low voltage. And then of course we have extra high voltage which is greater than 230,000 volts. So this is kind of gives you an idea of the volts that we deal with in our plants. And of course when you have a home, the service coming to your home is 15 kV or 5 kV. And then the service going to a small industry is 35 kV. Of course, put 3 zeros after that. But we just kind of stay with kVs. And the medium industry is 69 kV. And the heavy industry receives power at 115 kV. And we'll learn a little bit later here as to why the voltages change when you go to larger and larger industries. So now, of course, the counterpart of voltage is the current. So voltage is the level at which the power is coming, and amps is the juice. So amps is the A, and the product of the power is the volts times the amp. So that's the power is in watts is voltage times amps. If it is single phase, it is straight, kV times amps gives you the power. If it is 3-phase, then you have this little square root of 3 multiplier, because 3-phase has 3 phases of the power coming, and the total power that is available is greater than the product of the voltage and the current. So again, now when we have volts and amps power, then we start using MVA. M stands for 1000. So MVA is equal to 1000 kVA. So now we went from VA to kVA to MVA. So now we're getting larger and larger. And so the transformer is designed to change voltage. That's the primary function of the transformer. A step up, it increases the voltage. A step down, it reduces the voltage. And we will learn as to why we do either or one or the other in the industry. A control transformer is something we refer to in our industry as something which supplies small power, for switches and lights and those kind of things, and control voltage, very, very small. They're used in machines, small milling machines, lathe machines. Those are very, very tiny transformers. A distribution transformer is what you see outside your home or outside your library, sitting in a box, in a green box. That's a distribution transformer, very small size, because library doesn't take but maybe about 50 kVA, very small load. And then of course a small power transformer. Now we are going into terminology: small power, medium power, and large power. So these are our specific terminologies we use in our industry. So a small power is 15 MVA, and medium power is 100 MVA, and large power is greater than 100 MVA. And to calibrate us as to a 5 MVA, which is 1/3 of the 15 MVA. 5 MVA transformer will feed 1,000 homes. So a 100 MVA transformer will feed 100,000 homes. So these are very, very large transformers which provide a lot of power, and they are used for the incoming what we call primary substations. And that's where the power comes at higher voltage and gets transformed and then supplied to a complex industry, or generally in a residential or a city, whole city. So this is how the sizes go in MVAs. And so typical power rating, a house uses about 10 kVA, very small load. 10 kVA is a pretty good size home, maybe 5 kVA more general. A light industry like our plant here, our power is 300 kVA. We employ 350 people in this plant, and it's only 300 kVA. So a 500 kVA is significant transformer for an industry, and a medium industry will have 5,000 kVA or a 5 MVA, and a heavy industry will take 50 MVA power. A refinery, for example, may have 50 MVA or 100 MVA coming in, because it takes lots and lots of power to run a refinery. And then now moving on to a little bit electrical here in terms of phases. So a transformer has three-phase transformer has 3 windings. That's straight. And a delta winding is, as you can see, it's connected in a triangle, and we call it a delta. And a Y transformer, which is sometimes called a star, you can see why it's called a star. It has 3 legs, so it's called a star winding. So those are the two basic types of windings we are used for transformers. And a transformer has, each phase of the transformer, which is one of the legs that I showed you up there, has 2 windings in it. One is called the primary and one is called the secondary. So the power comes into the primary, which is power in, and it goes out the secondary. Very important to note, there is no physical connection between the primary and the secondary. They are not connected. So the power is transferred from the primary to the secondary by induction using a magnetic circuit, which is called the core. And that's the core. So in 3 legs, and 1 coil goes around each leg to make a 3-phase transformer. And this is how the coil looks like. So the center of the coil in a cutaway is shown as the core, and the core is in a stepped construction. It's also called cruciform because it is kind of circular and in steps. And then the inside winding is the low voltage winding, and the outside winding is high voltage winding, and there is always a gap between the two, which we refer to as a major. It's a big thing because these things should never touch, so it's a major. And then of course, as I mentioned earlier, it's oil-filled transformer and dry type transformer are the 2 types. Now there are standards for transformers because the industry gets together and says we need to write standards because we need to know how to design and test transformers, so the society understands that the transformer which carries a certain type of testing conforms to the industry standards. Our industry standards are written by IEEE, Institute of Electrical and Electronic Engineers, and it is enshrined in ANSI, American National Standards Institute. So they're the publisher, but the development of all standards is done by IEEE. And further, the transformer standard within IEEE always starts with C57. So the C57, which we call the division of IEEE, stands for transformers. So all transformer standards in IEEE will be found in C57. And then so we subscribe to the IEEE standards, and we have it on our on soft copy on our servers, available for engineers and salespeople to go and search for anything they are looking for. So it has then C57 and 12 is again oil transformers, and 00 is just the numerical reference to various standards under that C5712. And this 00 happens to be the general standard for oil field transformers. It defines a lot of things, and I will give you a glimpse of that later on today. And then of course the C571290 is the oil testing standard. The tests are prescribed by IEEE in saying this is what you will test. This is the level you will test it at, and it has to pass in this manner. So that's very important. All this is prescribed. Obviously, industry has to have standards, and public needs to know what they are getting, that it is complies with these standards. So that's how it is done. So now we have high voltage tests. So obviously it's a high voltage equipment, and it has to be tested, and you will get a chance at the end of your course to go down in the factory and be able to see our test floor where we apply all these thousands and thousands of volts to the transformers. And these are some names of the testing which is done. Again, this is all given in the IEEE standard, and then we test, every transformer is tested 100% to these standards. So now the 1251, the C5712 is common. 51 stands for the general dry type transformer, and the 91 is the test for the dry type transformer. Now it's very important to understand that in US we use ANSI, but the rest of the world, Europe, Asia, South America, all use what we call IEC, which is the European standard, and that's all everybody uses. US uses ANSI, Canada uses CSA. So, and we have our corporate manager has written a paper which kind of lays out the differences between those three standards. Now this is a, can we turn that?
Probably not.
I think we can rotate it somehow in here. Let's see.
View, maybe?
On view,
On view?
on top, on view,
Yeah.
but it's gonna do it for the full.
Yeah, I'll just rotate it back once I do that. Yeah. Display, zoom, tool, sign,
On top,
comment.
first one.
Rotate. Okay, good. Clockwise. Yeah. Okay. So now you see here, this is a sort of a diagrammatic presentation of how the electricity is generated and how it flows to the home or to an industry. So on the left top you see a thermal power plant, which are sort of going out of style as we move forward, but that is still the predominant source of energy produced in our country is thermal. So that's a thermal power plant, and the small transformer you see which is labeled a step up transformer. Step up. So the power is generated always at mostly at 14,000, 18,000, 17,000 volts, and then it has to be stepped up to a very high voltage. It can be stepped up to 230,000 volts, or it could be stepped up even higher, or sometimes at 130,000 volts. And the reason it is stepped up is because when you step up the voltage, power is a product of voltage and current. So if you step up the voltage for the same given power, the amperes or the current is less. And that means the conductors that you see in transmission lines will be smaller if you have higher and higher voltage. The transmission of power from the generating station to the consumer is typically 500 miles. So obviously you have a very long distance, so you want to use thinner wires, so you have less copper in those wires. That's why it is stepped up. And then of course it travels from there to a transmission substation where that 230,000 volts is stepped down to perhaps maybe 69 kV or 35 kV. And then from there it is further stepped down to a distribution voltage which is shown on the right hand side there in the middle of the picture. And it is stepped down from there to perhaps maybe 4,000 volts or 15,000 volts, and which is what then comes to the house. And that's where in the house you have a small transformer, which is the green transformer sitting outside in front or back of your house. And that's where it connects, and then that transformer changes the voltage to 110 to 20 is the dual voltage that comes to your house. For your washers and then dryer you have 220. For your plugs you have 110. So this is the route for the electricity to travel. So first we raise it to a very high voltage, then you step it down in steps. A substation and then another substation and then your distribution transformer. So it's very important to note, if you want to generate 100 megawatts, if a thermal power plant is constructed today for 100 megawatts, it's going to require 400 megawatts of transformers. So the multiplier on transformers is huge because it takes stepping up and stepping down. So that's the equation, that how it works out. And then of course we show this is the residential circuit, and of course similarly it also works for industry, the same distribution system. This is a small article here which Virginia wrote a long time ago as to why people want to use dry type transformer. And then basically there's cost element, but the most important thing is safe because it does not have oil. So if it is a defect or an explosion in the transformer, there will be no fire. So that's why dry type transformers are mostly used indoor in factories, also in inside the buildings, like or let's say the FBI building or World Trade Center. Those are going to have dry type transformers inside at every 5th floor or something like that. So that's where we use the dry type transformers. So it's a unique application. It is used for safety. It is used for indoor applications, and it is also used for longer life because it does not require any maintenance, has no oil. So you don't have to worry about leaks. Now this is I'm getting into now is the C57 1200. So this is the general oil standard, and all it does is it gives you lots of standards, like these are the standard voltages that you see on the left side for a single phase transformer. So if somebody wants to specify something other than standard, it becomes non-standard. So people will pick from the standard voltages. And then we can go from there and we can look at three-phase systems. And the three-phase systems has this kind of a table. As you can see, the voltage goes all the way up to 765 kV, which is 765,000 volts. And then, so these are the standards given in the ANSI. So the ANSI kind of specifies all the standards, and people who specify transformers, use transformers, must be familiar with these, so they know what is being said and what is being specified. So it has all this information in it. And now this I'm just getting into here is the comparison between IEC and ANSI, which is written by John, our corporate engineering manager. It's an IEEE paper. So this kind of outlines, and this is very beneficial to our customers because there are a lot of people who specify transformers who come from Europe. They are building a project in US and they're bringing an IEC spec. They say, can you build an IEC spec transformer? Yes, we can, because we know the differences between the IEC and the ANSI. So that's all this is. A lot of information on the standards and how they compare, basically. Now this here gives you an idea about the terminology we use in transformers, and there is a picture that goes with that. And in that picture it shows it's a typical oil-filled transformer, and it has these bubbles, and the bubbles point to what is in these. So if I can use this. I don't know if you can see that in Pocatello. I mean, that item 16 is a gauge. Item 18 is a gauge. So one is a pressure gauge, one is a level gauge, one is a temperature gauge. And then we have a valve there which is used for sampling air, because it has some air at the top of the transformer. So if you want to make a sample of the air to see if the air is nitrogen or the air is air, and if there is any moisture in it, those type of things. And then of course here it is on the right hand side, you see this part that is sticking out on the side there is called a bushing, which is where the customer makes connections. And same thing on the left hand side, you have a bushing for customer connections. And below the bushing on the left hand side is what is called an arrestor. An arrestor has a property to arrest high voltage. So in case by error or by some accident or by some transient there is a high voltage which is coming to the transformer which can damage the transformer, then the arrestor arrests that voltage and carries it to the ground. So it keeps the transformer safe. So this is just a general schematic of a picture of a transformer, and above that is the terminology as to what the different items are called. And then there's just another picture of that, shows inside what's going on. So that's the session 1. Kind of gives us an idea, overview of the transformer, standards, and the sizing and the terminology used and how it looks like, and the dry and the oil. So this is just the first session. Oh, there is a general handout here for kind of overview of a transformer. It's from a textbook. It's from a textbook, and then this is how in schematics a transformer is shown. You see these two circles which are overlapping. That means there is a primary and a secondary, and then those two circles show schematically a transformer when we make diagrams. So it's just the way the transformer is shown. So this is has a lot of information on it, the frequency, and then different frequencies in different parts of the world. So it will give you a very broad overview if you just skim through that. This is just as a reference document that I have attached here. So you can see it has a lot of information. This particular chart here talks about how the voltages, transmission voltages have gone up in the years. Back in 1900, most of the systems were less than 100 volts, and they have stepped up through the years. And now in 2000, or maybe really 1980s and 90s, we have gone all the way up to 1000 kV. In USA, we have a few places where we have 1000 kV transmission. So US transmissions mostly up to 500 kV, 345 kV. That's about it. There may be some 765, but not much. So 1000 kV is very common in Japan and China. Japan is the leading in terms of high voltage. They use mostly 1000 kV for their transmission. So their systems are more efficient. When we say their transmission systems are more efficient, how we measure that is the losses in the distribution and transmission system. In US, the losses in the distribution transmission system is about 8%. So in Japan, they might be about 5%. So that's the difference, but that's a very large number when you have 3% less losses in the system of distribution and transmission. So this is just gives you a lot of information on technical information of different materials used: copper, aluminum, steel, oil, etc., etc. So this will be something just for reference.